Okay, so in this mini lecture, we are going to look at the relationship between position and velocity. How do I get some velocity information from position information, and how do I get position information from velocity information? We're going to do that sort of together, both mathematically and graphically. And we're going to use the example of a constant velocity. And in this mini lecture and some of the subsequent ones, we're generating these ideas of our equations of motion, the ones that we can use to analyze and solve problems with kinematics, with motion. And so this is a case of constant velocity. So an object's moving at a steady rate. Now, if I have an object moving at a steady rate, let's say a rate equal to 1 meter per second. And I have that object moving for 1 second, so my time is equal to 1 second. How far is that object going to get in that 1 second? Well, if it's moving at 1 meters per second for 1 second, it's probably pretty clear that it's going to travel 1 meter. Well, what if that object was moving at 2 meters per second, so a little bit faster, and I still want to keep it moving at 1 second? How much position will it obtain in that 1 second? Well, again, if it's moving at 2 meters per second, and it does that for 1 whole second, it's going to go 2 meters. What if that same object, instead of going just for 1 second, that object travels for 3 seconds? So now it's moving at 2 meters per second, but it's doing that for 3 seconds at a steady rate. Well, it's probably not too challenging to deduce that over that course of time, it'll get a certain position of 6 meters. It will acquire, this is the position change that it acquires. So it will gain 6 meters if it's going at 2 meters per second for 3 seconds. It'll gain 2 meters, it'll move along 2 meters if it's going at 2 meters per second at 1 second. Or it'll move along for 1 meter if it's going at 1 meters per second for 1 second. If I want to generalize that into a relationship form, how did I get this 1 or this 2 or this 6? Well, I simply took its velocity, its constant velocity, and I multiplied it by how much time that object traveled. And so the velocity, my constant velocity, times the amount of time the object traveled tells us how much position the object acquires, how far it went in position. Well, that's great if I want to know where an object is going to end up at a certain amount of time, after a certain amount of constant motion has happened. How might I do that? What information would I need? Well, I would need to know how much position it acquired during that time. So I would need this relationship. But if I want to physically know where it ends up, I need to know where it started. So to get a relationship that gives me information about where an object ends, a final position, the position at the end of the motion I care about, I need to know where it started plus how much position it acquired. And this develops an equation of motion, one of the tools that we will be able to use to describe properties of the motion, perhaps its final position. So in general, for an object moving at a constant velocity, so no change in the object's rate, the final position is equal to where it started, the initial position, plus how much position it acquired, the constant velocity times time. Well, this should look very familiar to you in terms of the form. This is also the form of a linear equation. Now we're going to link our mathematical relationships to our graphical. A linear equation is a linear graph. This leads to a linear graph. And when we first talked about the graph of position versus time, we discussed a few things. We said that if an object is moving at a constant rate, then that's represented as a slope, a straight line, a linear relationship on a position versus time graph. So we're going to start to see how our mathematics is related to our graphs. So let's look at this position versus time graph that we have up here. And as we've talked about position time graphs, we can get some different information from them. So we can see that the object starts at a certain location, a location left or down or negative, whatever our negative direction is, negative of the origin. It already has a linear, that's not horizontal, a linear slope associated with it. We said that means it was moving and moving at a constant rate. So let's just look at this first part, moving at a constant rate. How can we relate this position versus time graph into something that's going to represent this object's velocity versus time? Well, we need to think about what that velocity means. Velocity is how far an object is moving in a given amount of time. It's a rate of change. And if we go back to the original definition of our average velocity, we remember that it was the change in position over the time of the motion. This time, this one piece of the time that I'm interested in, this change in time from the beginning of that time to the end of that time. Delta x over delta t, that looks awful familiar. That, if x is on the vertical axis and t is on the horizontal axis, that looks awful similar to our relationship in math class that was rise over run. The change in this dimension on a graph over the change in this dimension on the graph, that's the rise over the run. Well, that goes by another name. That's the slope. And what we see here is that our average velocity is the slope of the position versus time graph, the rate of the position versus time graph. And when we think about velocity conceptually, it's the rate of an object's change in position. They're related. So we can look at this graph and its slope, and that should tell us a lot about the motion and be consistent with what we know about that motion and give us the information for our velocity versus time graph. So we said that the object was moving. It is indeed moving. If it's moving, our velocity time graph, it's not going to have a zero velocity. It will have a non-zero velocity, a velocity off of that zero axis. Is it positive or negative? Should my velocity graph be up here or down here? Well, is the object moving to the right or to the left? Well, in our previous discussion, we said if the slope was positive, the velocity is positive, or it's moving to the right. Does that make sense with our slope relationship? Well, a positive rise over a positive run gives me a positive value. So during this part of the motion, the object is moving to the right. To the right is a positive velocity, and we should see our velocity graph developed above the axis, where these are positive values and these are negative values. Now, the actual value of this velocity depends on that rate, that slope. Perfect. All right, what does the object do in this case? Well, we said when this is meant to be purely horizontal, it's a little slanted. We said that when the object's not changing its position, we see a horizontal line on a position versus time graph. Okay, so a horizontal line on a position versus time graph, not moving, that means the velocity is zero conceptually. A horizontal line has a slope of zero. So during this part of the motion, the object's at a zero velocity. Great. Now, what happens during this part of the motion? Well, what do we notice? Is the object moving? Yes. The object is moving. We know that because the position is changing as time goes on. It's moving closer and closer to the origin. It was right of the origin, and if it's moving closer to the origin, that means it's moving to the left. We also talked about how a downward slope, represented motion to the left when we talked about the position time graph. If we look at the mathematical relationship of slope, the true velocity, our rise over run, we're going down as we move across. So we have a negative velocity to the left. They're about the same steepness, Maybe this one's a little shallower. And so if we're going to represent a little shallower slope, the distance between the axes and our negative velocity should be a little less than it was previous in the motion. So as my velocity graph is developed, my velocity values represent how fast the object is moving. If I'm moving slower in this phase than in this phase, I should have a lower value in this phase than I should in the first phase. Further, I'm moving in the positive direction during this phase, so I'm above the axis for velocity. I'm moving in the negative direction during this phase, so I'm below the axis in the velocity graph. So graphically, we can take information from our position versus time graph and turn it into our velocity versus time graph. Now, all of the motion here is constant motion, constant velocity, sorry. So I have a constant velocity, a straight line, linear graph. I have no velocity, I'm not changing my motion, so that's 0. Then I have a constant velocity, straight line, linear graph, again, but it's in the negative direction. So mathematically, when we talked about a linear equation, how we represent the mathematical interpretation of constant velocity, position information, position versus time is a linear graph. Position as a function of time in my mathematical equation should also be a linear relationship, and it indeed is. All right, so this is a relationship for constant velocity, and we're going to continue to work with position and velocity if perhaps I'm accelerating. Good job.